time collapse to zero size here. Whereas earlier, on some other hyperbola, r is not 0. And in particular, on the horizon, r is equal to 2m. So what we see is that inside the black hole, the shape of space itself is changing with time. R goes to 0 at a finite point in the future. Thus, we certainly don't have the usual kind of time translation symmetry. Okay? Now, it turns out, okay, so that tells you that energy is allowed to do funny things inside of a black hole. I'm getting to that, thank you. Well, there is no symmetry which acts locally inside here like a time translation symmetry. There is, however, a global symmetry of the black hole, which corresponds to time translations on the outside. Okay? And just to see that that should be true, let me quickly go back to the Minkowski space story. Or more properly, to what we called the Rendler story, where we looked at acceleration horizons in Minkowski space. Okay? Recall that this is an analog of what's happening near the horizon in the black hole. And that includes inside. Okay? So this space-time, it's Minkowski space. It has lots of symmetries. Okay? We don't want to consider the usual time translation symmetry because this picture is only a good description of our story there inside these hyperbolas, right? Close to the horizon. And if we applied a usual time translation, we'd move the hyperbola, so that wouldn't be good. But there is a symmetry of Minkowski space that leaves these hyperbolas intact. And that's a boost symmetry, right? The usual change of reference frames in special relativity, where we would change from some t x coordinates to some other observer, t prime x prime. If you're not familiar with this, let me leave it as an exercise. But the usual change of coordinates in special relativity from one orthonormal frame to another, from one observer to another, preserves these hyperbolas. It just moves points along them like so. Okay. So there is, this symmetry, in fact, does carry over well to this case. Okay. So there is a symmetry, and outside the black hole, in this region, you can see on the diagram I've drawn that it looks like you're just moving things more or less forwards in time, along a curvy path, but, close enough. So outside, it has all the properties you would expect of a time translation. But what about inside? Inside, it's sliding things horizontally. So inside, it has the properties one would expect of a space translation. Okay? And do you know what is the conserved quantity associated usually with space translation symmetry? Momentum. Right. So as a result, inside the conserved quantity is more like momentum. And it certainly wouldn't bother you if I told you I had a particle with negative momentum. Yeah. Right. Okay. So this is the basic flavor of the story. Inside the black hole, the quantity which interacts with what you would call energy outside is more like momentum, and it can have either positive sign or negative sign depending on which way the objects are moving. So the only trick is to get some interaction between the outside and the region where negative energies are allowed. So quantum field theory allows us to do that by basically having a small fluctuation where the energy is also negative outside, which lives only a short proper time and then hops inside to where it's allowed to persist classically. So if you like, it's a kind of tunneling effect. Only sometimes this is heuristically described as tunneling of stuff from inside the black hole outside. I find it much more useful to describe this as tunneling of negative energy particles from outside to inside. That's certainly the way that the energy flows. Okay. So that was a broad brushstrokes kind of picture. Didn't include many details. Is that enough for now? Would you like to ask more about it? That's okay for now? Okay. Very good. So let me move on. So this is the sense in which black holes have a temperature. Well, if they have a temperature, one might suspect that they would also have all of your other favorite thermodynamic quantities. Okay? And the most interesting thermodynamic quantity to many people is the entropy. So let's talk about black hole entropy. Okay? And I'm going to do a very simple calculation of black hole entropy for the Schwarzschild black hole. I'm going to do it using thermodynamics. You may recall the first law of thermodynamics, which says that the change in energy is equal to temperature times the change in entropy. Okay. Is this familiar to everyone? Is there anyone who doesn't recognize this? You might perhaps know this better as the definition of temperature. T is defined to be, usually it's written 1 over T is defined to be ds dE. Or you might know it better in terms of the definition of entropy. ds is equal to the amount of heat that flows into a system divided by the temperature. But it's all the first law.
You combine the first and second law.
No, this is just the first law.
How come you got entropy?
Perhaps it's a matter of convention, but in the way that I am used to writing the first law, one writes it in terms of entropy. Okay. Yeah. What's that? Yes. There are often other terms like P, dV, and so forth. Okay. So in fact, let me say it more precisely. I'm really going to do this not at constant volume so much as at zero pressure. Okay. Yes, there can be other terms. I'm also going to do it at, there are a few other things I'm holding fixed as well here. This is the simple form. Okay. Really, I guess you should say this is a combination of what other people might call the first law and the definition of entropy. So, yes, one might have written dq here instead of. Okay. All right. So, and I can do this because, of course, I know the energy in a black hole. The black hole we take to be at rest, so its energy is just m. Or if I hadn't set c to 1, it would have been mc squared. But I have set c to 1, so it's m. Okay? So, dE is dm. But it's also T ds, or in other words, ds is dE dm over T, which is dm, let's see, 1 over T is 8 pi m. So this is 8 pi m dm. So if I simply integrate this up from 0, making the rather natural assumption that a black hole of 0 mass should have 0 entropy, okay, what I find is that the total entropy in a black hole is, well, we can all integrate 8 pi m dm. It's none other than 4 pi m squared. Yes? Okay. Now, it's convenient to go back and express this in terms of the size of the black hole. And you may recall that the Schwarzschild black hole is a size r equals 2m. So what is this in terms of r? Well, 4m squared is just r squared, so this is pi times r squared. Oops, r squared. Okay. Traditionally, one writes this in terms of the surface area of the black hole. The black hole is a sphere of radius r, so the area is just 4 pi times r squared. So this is a over 4. Okay. And the reason one writes it this way is that although I have by no means proven this to you at this point, this is in fact the generic, or perhaps the general, expression for black hole entropy. That is to say, I have so far considered a particular kind of black hole, the Schwarzschild black hole, which is distinguished by, well, first of all, it lives in 3 + 1 dimensions. Second, it has no electric charge. And third, it's not spinning. It's just sort of sitting there in space. Black holes can have electric charge. They can spin. You can have more complicated versions in higher dimensions, all sorts of things. But it turns out that for any black hole, or black string, or black membrane, or black p-brane, okay, one can show in general that the entropy always takes the form a over 4. Okay. There is, in fact, a lovely calculation using the same Euclidean methods that we talked about earlier this week, which gives exactly that answer. And if that's of high priority to the audience, I can go through part of that calculation later in this hour. But of course, it will mean that we don't get to something else. Okay. So this is an interesting answer. Why is it an interesting answer? Well, first, let me just show you that it's consistent with things you know. Actually, I'm not going to do all of it, but I gave you on that list of exercises I hand out a homework assignment, which is to go back into these expressions for t and this expression for s and figure out where the factors of h bar, g, and c went to. Okay? I've done these calculations setting h bar, Newton's constant g, and the speed of light equal to 1. Okay? But it often helps physically to understand where they are in these expressions. I will leave that for you to sort out. It's just dimensional analysis. But I will tell you 2 interesting properties of what happens as h bar goes to 0. First thing that happens as h bar goes to 0 is that the temperature of the black hole goes to 0. That's good. After all, I claimed that this Hawking radiation was some kind of quantum effect. Okay? The second thing that happens, which actually you can guess from the first one, you notice that S involves 1 over t. So if t is going to 0 in the classical limit, you would expect that the entropy goes to infinity. Okay? So there are h bars hidden in this expression such that in the denominator, such that as h bar goes to 0, the entropy becomes infinite. Right. Yes. Okay. Maybe I'll even show you this h bar just for completeness. I'll show it to you first in a place where you know it exists. If I had done not Euclidean field theory, but Lorentzian field theory, and looked at this object, where's the h bar here? Where does the h bar go in? It's h times t divided by h bar, right? Okay.